Hello and welcome to Noel's Retro Lab. Today we're going to be looking at the Amstrad GX4000. Yes, this is the first time we're looking at a game console in this channel. And this was Amstrad's last-ditch attempt to make a console right at the end of the 8-bit family life. So join me today as we learn more about this console, open it up, and hopefully fix it. So here it is, the not very well-known Amstrad GX4000 console. I actually bought this one as not working, so at least it won't be any surprise when it really is not working. And it didn't even come with power supply or game controllers or anything. Other than that, it's externally is in pretty good shape. There's nothing obviously broken, and it's very nice and compact and small. It's pretty good. Has a lot of ports, so it has ports for 2 game controllers in the front, and I think that's an analog joystick. This is stereo sound. That other one, it's some kind of peripheral. And then in the, well, it has a cartridge slot right there. That's the on and off. And then in the back, so it has a very curious design decision right here. It has 2 power jacks. It turns out one is for 11 volts and one is for 5 volts. And yeah, it sounds like a horrible design idea, right? At the very least, this one is smaller than this one. So you can't just accidentally plug in the 11 volt jack into the 5 volt one, which would just blow the machine up. So, well, no, but it would blow the memories and transistors, and lots of bad things would happen and release the magic smoke. They did this supposedly so it would work with the monitor sold for the Amstrad Plus line, which then would use that video output. And you could also use an external power supply, 11 volt power supply, and then you would use it with the SCART video out. And then that is probably an RF out for video in case you still wanted it. The GX4000 was Amstrad's first and last attempt at making a game console. It was an 8-bit console, but it was backwards compatible with the Amstrad CPC line. Actually, more than compatible, it's more like it was the same architecture with just a few new features added. It had hardware sprites, much needed. It had more colors available, which is great. They added DMA for sound generation, which we'll see in a future video. And then of course they added loading from cartridges instead of discs. Amstrad also released the Plus line of microcomputers at the same time as the GX4000. They had the same features as the GX4000, plus they were a microcomputer, so they had a keyboard and you could program on them. In theory, all of this sounds like a nice upgrade over the basic CPC capabilities, yet the GX4000 and the Plus line, to a certain extent, was an absolute commercial failure. So what happened? This is a perfect example of too little, too late. The GX4000 was released in late 1990. To put this in perspective, this is a machine with pretty much the same technology as the Amstrad CPC 464, which was released in 1984. That's 6.5 years earlier. 16-bit machines had been around for quite a while at that point, with the Atari ST released in 1985 and the Amiga 500 in 1987. Now, those were clearly much more expensive machines, but still, that was many years before the GX4000. So how about some more direct competitors like game consoles? The Nintendo Entertainment System, which was also an 8-bit console with capabilities not much worse than the GX4000, was released in 1985 or 86 in the European Union, and the Super Nintendo, which was an amazing 16-bit console, was released in Japan only 2 months after the GX4000. So yeah, it never stood a chance. And it's no surprise that Amstrad never attempted to make another game console. Okay, so it's time to open it up and see what we find inside. Oh, that's right. I remember this now. This is a really nice design. I think it only has 2 screws. I always appreciate when consoles or computers are easy to open and minimize the amount of screws. So yeah, it's just that, and now I think it's just the tabs. This is just the on-off switch, so we'll be able to unplug it and bridge it. Oops. And right, this doesn't even have any screws. So nice. So 2 screws to take out the whole thing. Yeah, that's how I like it. From a visual inspection point of view, everything seems fine. It's a little dirty, but the caps are all fine. I don't see anything obviously blown up or black. The back looks totally fine. Let's have a look at the board of the GX4000. There on the left, we have the Z80 CPU, just like in all the other Amstrad CPC computers. There we have the gate array, which is a custom chip with, like 160 pins. And that combines a lot of the logic that before we had in discrete chips, like a CRT controller and input and output processing and clock generation. It's all combined in that big chip. There on the right, we have the RAM with 2 banks of 32K each. We have the same AY chip that we see in other versions of the Amstrad computers. And then we have a couple of small chips. One is the video digital to analog converter for the video signal. And then we have an RGB encoder, which is used to generate a composite video signal that gets fed into the RF modulator. So really, there isn't much to this board. Almost all the functionality is contained in the gate array and the Z80. For our test, we're going to use the 11 volts jack, which is the normal 5.5 millimeter DC jack connector. And we'll also connect it through the SCART connector to the TV. As usual, whenever possible, we're going to test it with a bench power supply because it's going to show us what the actual current draw is. And since I know that's a potential source of problems in this kind of consoles, it's a good thing to check this. So we're going to set it to 11 volts and up to 1.2 amps, which is plenty to drive this console. It is hooked up this way because it's center positive, like most power supplies of this type. And if we turn it on right now, we're going to get no current draw whatsoever because I still haven't bridged the on switch. So just as a test, yeah, we're getting pretty much nothing. So let's put a jumper there. So I'll just put in a regular jumper like that. If all goes well, now the voltage should stay at 11 and we should get a current draw, I don't remember, maybe 0.5, 0.6, something like that. Oh, that is not good. I'm turning it off. So that was 5 volts and the current was maxed at 1.2. So that means we have a big short, which means it's probably this initial voltage circuitry that I was telling you about earlier. So this is what the voltage regulation circuit looks like. It looks pretty messy, but that's because we have the 2 inputs. We have the 5 volt input and the 11 volt input like we saw earlier. Let's put this side by side with the board itself and just rotate the board to the left so we have the inputs on the same side, just to get oriented a little bit better. And so when we look at this, the 5 volt input goes through a coil and then pretty much goes straight to the switch. There's nothing else to it. The 11 volt input goes through the 7805 voltage regulator, which we've seen in plenty of places like the old ZX Spectrums, and it gets pretty hot, so it has its own heat dissipator. And the output of the 7805 then gets connected straight into the same line as the 5 volt input. Interestingly, the 11 volt input also goes through a different voltage regulator, which also generates 5 volts, but a much smaller current, only 0.1 amps. The output of that is also 5 volts, but that is kept separate from the main 5 volt line. And I believe that's being fed into the video DAC that generates the video signal that goes on the SCART connector. If some of those voltage regulators fail and they short, the 11 volts now spread everywhere. So horrible things can happen. This is a fairly fragile area of the circuit in this console. So it's always worth looking at it very carefully, sometimes even before powering it up. Looking at the circuit diagram for the initial voltage regulation, it's clear that if something had gone wrong with one of the voltage regulators, we would see the short before the actual switch. And actually I turned it on earlier and it seemed to be fine without the switch, but I'm gonna remove the switch. So it's going to be, the machine is going to be switched off, but the voltage from the power supply is still going to be going there. So we should see a stable 5 volts in one of those pins and ground. So we have the bridge that we put in the switch removed, and I'm going to turn on the power supply. And I'm going to measure, first of all, just the input, just to make sure. There we go, 11. And then in one of these pins, there you go. That's perfect 5 volts. So yeah, the voltage regulators seem to be working fine. That doesn't seem to be the problem. The problem is somewhere else on the board. Some very likely candidates for having a major short are the memories. So we could try turning on the power supply and with the bridge back on and seeing if they get hot. Another possibility could be the Z80, and the worst possible case could be if this ASIC, the gate array plus whatever other logic, it has the short. That would be close to irreplaceable. I have replaced them in the past, but it's not a fun task. You're better off, if you can, just put in a new board. So let's turn it on and see. It's only been on for a few seconds and these memories are already getting hot. So I think it's pretty safe. Let's remove them and socket them. That's not a big deal. And then we can even turn it on again with them removed. Obviously nothing is going to work, but if the voltage remains stable, then the short came from there.
We'll start by desoldering both RAM chips. These two came out beautifully. I don't even have to retouch them, they come right out. Then we fit new sockets and solder them. And of course, as usual, we clean the flux with some alcohol.
Okay, so I've removed the 2 RAMs. The bridge is on in the switch. We're at 11 volts. Let's turn it on and see if we manage to get a stable 11 volts there. Much better. The voltage is stable at 11 and the current draw is only 3.6, not 3.6, 0.36. So that's great. Let's put on some new memories and test it. Before we can actually test it, we need to put in a cartridge. Otherwise, we're just not going to see anything. So, like that. And we still get no image. As usual, the first step is to check that we're getting the right voltages. So let's start with the Z80. Z80 gets 5 volts and pin 11 should be this one. Yep, that's good enough. And the Z80 is really on the other side of the board from where the power jack is connected. So if it's powered up correctly, chances are everything else is fine. We even see the LED as an indication. So, the voltages look pretty good. As usual, the next thing would be to check clock signals. And let's start checking right in the CPU. So on the Z80 is pin number 6. Right there. Oh, that's not looking good at all. That's totally flat. Okay, let's just randomly check some address line. Nope. And some data line. Nothing. So there's no activity there whatsoever. We need to track down to see where the clock signal is coming from. Unfortunately, it looks like the clock generation happens in this big chip, like many other functions on this board, since they've taken a lot of the logic that was on the board in earlier versions of the Amstrad CPC anyway, and moved it out into this big gate array as ASIC chip. And the clock generation is one of them. So there's the crystal oscillator there. It gets sent to the gate array, and then it generates a clock signal that goes to the CPU. So we can try to see if we get an input, very small signal, and this is in pin 2, and it's a little tricky to get exactly the right pin. So that should be the one. We're definitely getting something. I'm gonna zoom in. Yeah, so that looks about what I would expect as an input. So that's the input. So I think the crystal oscillator is fine. Let's look at the output. The output clock signal from the gate array, it's on pin 16. There's one of them. One of them is in pin 16. It's called clock 1. And there's a clock 16 and pin 117. So maybe this is a 1 megahertz clock signal. And pin 16, it's tough to get it right here. There it is. That's a 1 megahertz clock signal coming out. Okay, that's encouraging. Right, but clock 1 is a 1 megahertz signal. That's not going to the CPU. The CPU gets a 4 megahertz signal. So there's another output on the gate array, which is pin 125 that is labeled clock 4. That's the one. And that is getting no signal out. Make sure I got the right one. 2, 3, 4, 5. This is definitely 125. And there's nothing. I was hoping that maybe there would be a signal there, and then this particular pin wasn't attached correctly to the rest of the board, so it wasn't sending the signal. But no, it looks like it is not generating that signal at all. So unfortunately, it seems that the problem is the gate array. In this particular form, it's very difficult to replace, and even if you had a replacement, you might as well just replace the whole board. So that is one of the main problems with those kind of chips. And that's why I also like to repair computers earlier than this one, like mid-80s or maybe 87, 88. All the chips were more like the through-hole components like these, and they're easier to replace and test out. So it's unfortunate, but I don't think there's anything else we can do with this particular board. So I'm just going to have to save it for parts to repair other boards. And so we were not able to fix this console. That just happens sometimes. I already warned about it last week when we kind of fixed the ZX Spectrum Plus 3, but I had to replace whole parts. This time we can't even do this. It's the ASIC chip, and that just happens. And the more modern the hardware is, the more that can happen because they tend to integrate more and more functionality into large custom chips like that sometimes you just can't replace. In spite of that, I hope you still find it interesting. We did some troubleshooting, we detected some things, and we repaired that memory. But in the end, we were just not able to get it functional. If you enjoyed it, please still give it a thumbs up and subscribe to the channel. Until next video, see you then.